And of course, thank you all for coming and enduring a relatively long Saturday morning. We've seen a lot of theory, we've seen a lot of proofs today. The only thing that I can guarantee you is that there's no more proofs in this talk. So we're switching to something entirely different. And yeah, when Martin asked me to play a small role in INSAIT, I was super excited. I'm also super excited to be here to have the opportunity to talk to you. I'm driving this point home because I'm going to start my talk with a slightly provocative question to wake everyone up. Right? And that question is, why did I have to come here? Right? I'll wait until at least one of you looks semi-offended, and then I'll change that question to, do I need to be here in person? And by that I mean physically. Of course, I want to experience the same situation, the in-person situation, but maybe I do want to do this without incurring the tax in terms of carbon emissions. So the flight Zurich to Sofia emits the equivalent of 0.5 metric ton of carbon dioxide. I don't know how many of us flew. The average budget that we have to keep the planet in a safe envelope is 0.9 metric tons, so we're pretty much done with our budget for this year. And so then the question arises, can we combine the two ideas, being together, experiencing the same thing, and not having to fly everyone around the planet? So kind of the vision stolen from Disney here, or George Lucas, would be that we can be in the same space, either a physical space or some virtual space. We can appear in a lifelike fashion. We can potentially, parse body language, parse all the richness of human communication without having to travel over large distances. And so the technology behind this, in principle, exists. It's not as polished as you would see it in the movies. So how do I know? Well, Martin alluded to it a very long time. I had the chance to work with excellent people on a pair of papers that allowed you to really reach into virtual scenes and manipulate virtual objects in a natural as possible fashion, and in reconstructing your world in real time using only a commodity depth sensor, which is known as Kinect. And these two papers played a small role in nudging forward what is now known as Microsoft's HoloLens project, which is, I believe, the first commercially available augmented reality headset. So this is basically a pack of sensors, or a set of sensors, and a display that you wear in front of your eyes that allows you to see registered 3D graphics that are embedded in the real world. This is very, very difficult, very advanced technology, the intersection of computer vision, computer graphics. You're fighting with physics left, right, and center. You have to do a lot of computations. You have to do that on the body, and you have to move away a lot of heat that is the product of all these computations, and you have to get all of them right in order to get a good experience. So what I want to talk about today is not a product from Microsoft, but is actually the computer vision side of this. And in particular, the computer vision side of perceiving humans so that we can basically reproduce them in a different location. So the question then is, what would it take to make fully immersive telepresence a reality? And so there's three main requirements, in a way, that pop out from this constraints of having a display and a set of cameras that you're wearing on your body. So if you look at this illustration here, you see that we have a fairly dense social situation. We have people wearing complex clothing. We have people partially overlapping each other. And then you want to basically scan them in using only a single camera, or maybe two cameras that you wear on your body. So we require systems that are robust to visual complexity and that work in unconstrained settings, right? We cannot first install like multi-camera system before we want to quickly chat to grandma. So such systems then need to be able to reconstruct us in very high spatial fidelity. Today, what you need to do is you need to first have a template and then register this template to observations. So you can get high fidelity geometry, but you can't get it in unconstrained settings today. And beyond detailed reconstructions, we also want like the underlying parameters so that we can later control and retarget. So in a way, if I know how to control a scan that I created of you or myself, then I can put myself into a different physical environment, retarget my motions, and together reconstructing, controlling, and some kind of advanced rendering technique would allow us to generate a virtual mini-me of myself. And so that's kind of the personal motivating scenario that drives a lot of our research. Just in case you're not convinced, I want to point out that the underlying techniques and algorithms that I'm going to talk about today are not only applicable to this scenario, right? So in essence, the high-level goal of my research team is to develop methods that understand human activity, human pose, human appearance, such that advanced AI systems can interact with us in a natural as possible fashion. So here are some potential examples. I started out with the telepresence, AR telepresence scenario, but if you think about AI systems that operate in the emergency theater in a hospital, that operate in the home, for example, healthcare robots or self-driving cars, they all have to deal with this close social interaction with complex geometry and occlusions, and of course high fidelity geometry and appearance. So yeah, overall my team in Zurich does research in three main areas. The first is human state estimation, so that would be figuring out what is the hand pose, where are we looking at. All of these are useful for many applications in robotics, but also would be fundamentally important for such telepresence applications. I've already talked about reposing and predicting what people will do. This is the second leg of our research work. So basically, once you have an initial state estimate, you want to have probabilistic methods to tell you what are possible futures of an individual or several individuals. And then the last block, and that's going to be the backbone of the talk today, is what's now often called virtual humans, and this is really like high fidelity reconstruction of shape, appearance, and often generation of new behaviors. Yeah, and so that third part is basically what I'm going to talk about for the remainder of today. So you may ask yourself, like, why do we need new techniques? Is existing work not enough? You may have seen things like SMPL. This is a statistical body model. It's been tremendously influential in human pose estimation because you can basically use this model to predict the parameters from images and then do tasks such as pose estimation, which you've seen here. The pros are that such models generalize and work fairly well for a lot of methods, but they lack details and they're very sensitive or are known to be sensitive to visual complexity. So this is just footage taken from a well-known TV show, and really highly accurate methods start to fail due to the occlusions and cropping effects that you see. On the other hand, if you have a personalized template, so if you have like $1 million 3D scanner that can acquire the geometry of people, you can then use this geometry to fit it to videos, to fit it to a sequence of images, and that gives you a very nice reconstruction, but it requires that personalized template. So here, generalization to in the wild settings where we haven't seen the subject beforehand is difficult. So what we want to do in our work is basically have a detailed model of humans that can capture high-frequency geometry, appearance, but also generalizes in the same way as statistical models. So now this is a non-trivial wish list because extending simple to really capture things like hair or clothing is non-trivial. You cannot just scan the entire world, and that's why you cannot just mush them together and get something that works. So what we're proposing is basically a modern approach to analysis by synthesis, where you have a model that allows you to draw samples of virtual humans, and then you try to fit these to two observations. At the core of it basically lies a learned parametrization of humans in the canonical space. And this definition in the canonical space is fairly important for the generalization, and I'll show you later what I mean by that. But in the end, we're representing people by neural networks that predict shape and that predict a continuous field that tells me how every 3D location on the body in this canonical space will deform. Once we have this model, we can take, for example, video or a stream of depth camera images and perform latent space optimization at test time to find the parameters that will give us a 3D reconstruction of the input of the observation. So this is really a traditional technique in computer vision, kind of reinterpreted with very modern, very state-of-the-art tools. So the main research question that I do want to go in a little bit of detail is how do we actually get this representation of people? And the thing that may not be obvious to everyone is that it's fairly difficult to actually get people to get into a predefined pose repeatedly. So there's a technical or practical difficulty in acquiring data for supervised learning methods. So what we've developed over the last couple of years is basically an unsupervised learning technique for such neural human representations that learns from post observations only, right? So you just take video or depth images, and then you try to find this canonical representation, both in terms of the shape and how these things deform over time. So if we have a deformed point xd here on the left-hand side, the question becomes, what is the correspondence in the canonical frame? And the answer to that, or our secret sauce, is basically a 3D correspondence search module, which runs an iterative optimization problem for a lot of 3D points and basically inverts this question. It says, for different canonical points, if I deform them with, for example, linear blend skinning, how far are they away from my observation? And then basically those that converge to a very, very small distance metric, those we assume to be the canonical points. Once we have these canonical points, we can pass them through a shape network that's post-conditioned, and this will produce the reconstructions in the 3D space. This whole thing basically has two models in it. There's the shape field over here, and then there's a deformation field, W, within this iterative optimization. And that actually makes this whole thing tricky, because for every iteration of the optimization problem, you have to query a neural network, and you also have to backpropagate the gradients through this iterative process. And that is non-trivial learning problem. I want to unpack this a little bit more, because everything else that I'll show you today is built on this 3D correspondence search module. So in the essence, what this black box does is, as I said, we sample many, many points in the canonical space, here shown in blue and green as two potential candidates. In practice, we sample over 10,000 points and then initialize them by deforming them with all bones in your body, and then run this iterative search problem, which can be solved with quasi-Newton methods, Broyden's method in particular. And then those that have paid attention here, those of you that have paid attention, will see that there is a situation where there's self-contact, right? The hand in post space rests on the hip, And that means there's several canonical correspondences on the hip and on the hand. So this optimization problem will actually have several valid solutions. So what we do is that we basically rigidly transform each query point with all the bones in the body, and then collect the valid solutions by convergence. Right? Some points that are close enough to a plausible 3D shape and that deform in the correct way will actually converge, and other points that are somewhere in free space will diverge. And so we're taking this, this set of converged points as our canonical points, canonical correspondences. And then the rest is relatively trivial. We take these canonical correspondences, feed them through the shape network. This is conditioned by the input pose, so knowing the human pose, so the state of the joint angles is one of the inputs to these methods, and then the shape network will produce the final 3D shape. So conditioning it with the pose means that you have basically nonlinear, or can capture nonlinear deformations due to the poses. And then a simple operation at the end combines all these predictions, which then gives a continuous 3D surface. In the case of occupancy networks, which you see here, this would be a max. If you parameterize the shape with the signed distance field, this would be a min operations, but for different surface parameterizations, there's different valid ways how to do that. Yeah, and then maybe the last problem, I already alluded to this, is that we have to backpropagate through this iterative correspondence search, and luckily via implicit differentiation we can attain an analytical gradient that allows us to actually do this and train both the shape network and the deformation field in an unsupervised way. So let's look at some results. First, this is the basic paper, or the initial paper that kind of proposed this 3D correspondence search. As input, we take post 3D meshes, so this actually comes from a 3DMD $1 million 3D scanner. And from these meshes, without any additional supervision, in particular no skinning weights, we learn these canonical representations. So we learn what the surface is and how the surface deforms. And then at inference time, you can put in any pose you want, and you get high fidelity motion out of this model. So let's talk a little bit about generalization. First, I'm going to show you the training data. These are the training scans, played back relatively quickly. And then once we try to reconstruct novel poses, but from within the training distribution, ours, which is the second from the right here, works pretty well, but so do existing methods. There's some artifacts in backward skinning and in NASA, which are earlier approaches. However, as soon as we go outside of the training distribution, so now we're testing with poses that come from a completely different data set, you'll see that ours will generalize and degenerate quite nicely as you go far away from the original pose, but there's quite some nasty artifacts in existing methods. And this really comes from the property of having defined the deformation field in this canonical pose, because now the deformation field does not depend on the pose. So these are kind of minimally closed humans. Most of us, most of the time, wear clothing. This also works for at least relatively tight clothing. So this is the CAPE data set. Again, several poses, now wearing t-shirts and shorts, and then the reconstructions, the learned skinning weights and the learned deformation, again with poses completely outside of the training distribution. Likewise, someone else kind of climbing up and down a set of stairs. So this is SNARF, that's the name of this method. And it enables learning of canonical shape and skinning weights from deformed observations only, so in a completely unsupervised way. And it allows us to generate continuous shapes, and it has this nice property of generalizing to completely unseen poses. However, there's lots of limitations, right? We require full 3D scans for training. We require many poses of the same subject. It does not model appearance, so no color, no texture. And it's a subject-specific model. So we train one of these models per person. Training takes days. So it's not exactly practical at the moment. Yeah, I'll take these limitations as a quick to-do list, and then without going into much technical detail, we'll basically show solutions to almost all of those limitations, or at least solution approaches. First one is a paper called PINA from this year's CVPR that basically takes this 3D correspondence search module and applies it to the setting of depth videos. So depth is very different from complete scans. You have a single camera that you're pointing at someone. The data that you get has 3D information, but it's much sparser. It has only information on the surface. You have no supervision in free space. You'll have lots of missing observations. In this frame, the whole head is gone, and obviously the back of people will not be visible in individual frames. So dealing with these challenges is basically possible due to the fact that we now have a canonical reference frame, and we can fuse the information. We can fuse this partial and sparse information into a single canonical representation. I said not too many details, so basically the method consists of a global optimization that takes depth and images as input, uses the correspondence search module that I just introduced to transform the deformed points into canonical space, learns a deformation field again and a signed distance field of the shape, and then compares the produced post 3D shapes and normals to the input. And here the learnable parameters are again the skinning weights, the shape, and the pose itself. And really optimizing everything jointly is what makes this work. So now, basically, we can take a short video sequence of a single person, and then that's our entire training data. So I'll play the training data for this particular model in its entirety, and then the learned model is now being reposed. So we take poses from some other data set and re-render. This is Juan, one of the postdocs in my group. I don't know if he can do speed vaulting in real life, but now at least virtually he can do it. So that's kind of an extension that all of a sudden allows us with commodity hardware to produce at least like geometrically accurate avatars within a fairly limited time budget. But as you've seen, it's kind of this rendering of just the 3D surface. There's no texture, there's no appearance information, which clearly as a human being is very important. So I'll briefly want to talk about another CVPR paper, also from this year, everything brand new here. It's called I'm Avatar, and basically does what it says in the tin. It learns a facial avatar, this time with appearance, just from videos. There's no depth information here. There's a bit more of an assumption on where the camera was, what the lighting situation was. What you see here is different members of my group. And this is actually generated sequences, so they haven't gone through these head poses and these expressions. So the problem setting really is training from video with neutral expressions, so just talking people, and then we learn an avatar that actually extrapolates to expressions that you haven't seen before. The method itself, again, builds on the 3D correspondence search module. Maybe one thing that's interesting here is that faces are not predominantly driven by skeletal deformation, but you have a lot of soft tissue, tendons, and a lot of expressivity in the expressions. So we build on computer graphics models and learn, let me see if I can quickly abuse this. No, I can't. Learn another set of continuous fields that model these expressions. And once we've learned these three continuous fields, we can use them to control expressions. So we can make people smile and open their mouth and blink their eyes and whatnot. Another aspect that's different from previous work is that here we're actually doing ray marching. So for every pixel, we have to find first the intersection of the ray and the surface, and then find the canonical correspondence. Once we've found the canonical correspondence, we can query basically the RGB value for that location in the generated image. And another neural network will then predict what the final color of the pixel should be. Now this differentiable rendering module here on the right-hand side in itself, again, is an iterative process because it also needs to march the rays. And here we provide a formulation that decouples the dependencies of these two. I won't go into any details, but what you should remember here is that there is an analytical gradient formulation for the color network that basically factors out the deformer, so at least the two iterative processes are independent from each other, which makes this whole thing tractable. Okay, again, a few results. As I said before, these are generations, so artificially induced expressions and so forth. And Drago talked about NERF, so that's a volumetric rendering technique. This is a surface rendering technique. NERFs can also produce pretty pictures, but typically if you look at the geometry, it's pretty bad. If you look at the geometry here, you see that a lot of the spatial detail is actually present, and you could use this directly in computer graphics applications. Okay, so the last check mark from my to-do list today is that all of what you've seen so far is a subject-specific model. I'll go even faster on the last project or paper if you want. So that's called GDNA, and that's really a work in progress if you want, where we develop generative models of virtual humans. So basically you have a distribution, you sample different identities, and then you inherit the post-control and generalization capabilities from SNARF. So this allows us to really create new people and remote control them if you want. The pipeline itself steals ideas or borrows ideas from 2D generative models, which first produces this canonical shape, and then a multi-subject version of our 3D correspondence search, which transforms the canonical representation into post space and also adds personal details. I'll show you some of the generations here, and then just to make clear that we're not just memorizing the training data, on the right-hand side, you're always seeing the nearest neighbor in the training data. And so there's a lot of variance in the clothing, there's even different styles of wrinkles, male subject, female subjects, and whatnot. And the main reason why I'm showing you this is because this is really opening up a new direction for computer vision and goes back to the original idea of analysis by synthesis. So what we can do now is we can draw samples from this model and then fit them to observations. So here is basically GDNA extended with a simple network that also predicts color. And then you can optimize the parameters of this decoder so that it fits an observation. In this case, this is also a 3D scan. Another single static scan, this comes from a publicly available data set, where we fine-tune basically the generation from GDNA and then have an animatable model from one frame or one observation only. And this is really ongoing work, but I can already tell you that we now have evidence if you do this with images, so you solve the whole pose, shape, appearance estimation problem jointly, you actually get better results for the underlying 2D tasks. So you get better segmentation, you get better poses, and you get nice 3D models jointly. And so that's basically the to-do list for today. And with that, I'd like to thank you. And